universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hey, folks, welcome to Skyter Radio. Is I, Mark D'Antonio, and that guy over there, that's our esteemed producer, Bill Skywatcher. Hey, Bill, how are you?
What's up, Mark? How's everything?
Good, good. You know, I wanted to mention to you and to everybody else that tonight we're going to be doing something interesting. But first, let me tell you a little bit about Skyter Radio. And Bill's the perfect person to have on tonight because I don't remember when we started. When did we start, Bill?
2017, I think.
Maybe it was 2017, maybe it was 2016. I don't remember.
I think. I'm not sure.
I don't know, but you know, it's been like a whirlwind. We've just gone and gone and gone, you know. And so we started with Skyter Radio, and Skyter Radio was kind of an offshoot of something else that I was doing, and that was Skyter live stream. Now, Bill's been here. He's come to this location. He's seen the dome on the front lawn that people in the town see, this big dome on the front lawn of a house. You know, what the heck is that? And it's Observatory, right? And I'm an astronomer. That's what I got my degree in. So I spend my time trying to get back to astronomy in a way that can be helpful. And I'll tell you a little bit about some discoveries that were made using Skyter live stream data. Actually, that's something that happened. So that said, you know, Skyter live stream is a wonderful place to go on clear nights. I'm in Connecticut. The observatory is 2,500 miles away in the Arizona desert, and I run it from Connecticut. So it's really creepy to watch, you know, a building open out there because you press a button 2,500 miles away, and then running the telescope. Right, you've seen it. You know what it's like. It's kind of weird. It's like, man, this is really happening, right? Because it was only a few years ago when we didn't really have a technological capability to do that in general. Well, now it's gone so fast and so in such leaps and bounds that not only can we do that, but we can do it from the middle of the desert where there's one, no power, and two, where there's no internet. But we have power and we have internet. Now the power, it's a fully green observatory. The power comes from the landowner's solar panels that he has on the property. Okay. Now he and his wife built this solar field of panels basically, and they use it to get their power. And so they graciously allowed us to tap into it. Now we don't use a lot of current in the middle of the night when we're using the telescope, so it looks okay. It works okay, you know. So
and the internet is Starlink.
Yeah, the internet is Starlink. Yeah, and one of our amazing contributors who works with us as an official volunteer for Skyter Livestream is a guy named Mike, and he works at SpaceX. And Mike and his girlfriend Tiffany are the ones that orchestrate the exclusive giveaways of equipment. We offer telescope equipment, binoculars. Don't start drooling now, Bill. You just sit down. Okay. And they chose Skyter Livestream as their exclusive outlet for giving away this equipment. So we'll be at Contact in the Desert, okay, in June, early June. And we'll be at Roswell. We'll be in Arkansas at the Ozark Mountain UFO Conference, although their internet there is not very good. So I won't be able to do a live stream from there, but I will be doing live streams from Contact in the Desert and live streams with Skyter Livestream in Roswell. And in both places, we'll be giving away equipment. And exclusively in my talks, my presentations, we're going to be giving away several sets of binoculars and entire telescope systems for the people who attend the talk. Is that bribery?
Nah.
I mean, it's sort of, you know what it is? It's forcing people to accept that someone wants to teach them science. I'm not trying to ram it down their brains, but you know, I think it's important to consider that astronomy currently allows people who are amateurs. Now, I'm a professional astronomer, but people who are amateurs can make amazing discoveries. I'm going to give you an example of one right now. Back in 1952, there was a photograph taken of an area in space, and you saw the stars. And then just about an hour or hour and a half later, another photo was taken of the same location, and some of the stars were gone, missing. Wait a minute, stars don't just vanish. They can't move that fast. They just simply don't do that. I mean, because they're so far away, it takes decades for some of these more distant stars to see the slightest bit of movement. Okay. However, these stars were gone. And Beatrice Vieiro is an astrophysicist woman I know who's started a program to try to identify these missing stars and where they went and if they were stars. And Isabella, who is part of our SkyTour live stream, was so taken by this prospect of finding missing stuff that she went through all the past or many of the past imagery that we've done with SkyTour live stream. And don't you know that she found things in some of those images that aren't there today? She
Wow.
actually found them, and she actually was very diligent. She's in Bulgaria, okay, but it doesn't matter. We're a worldwide phenomenon. So she went into the data and she found successive images of the Pleiades in this particular case, and she found a star that shouldn't be there in the Pleiades, and it turns out that it was an asteroid, and she discovered this asteroid going through the Pleiades. I mean, that's pretty cool, you know. Now, she didn't discover the asteroid; it was a known asteroid, but it was she basically noticed that there was an asteroid in the field.
Well, we should call it Isabella regardless.
I want to call it Isabella 2023.
There you go.
Because I think she discovered it. Oh no, it would be Isabella 2024 because it was this year. Yeah, so that'd be kind of cool. Of course, unfortunately, even if we do make discoveries, we're not allowed to name them. The International Astronomical Union does that. But it's interesting how this works, you know. So Isabella made this discovery, and if she's listening right now, she's probably going, "Oh no," you know. But it's true. And if Michael and Tiffany are listening, they're going, "Oh no, he mentioned us," you know. But the fact is, they're all very humble, and they expect nothing for what they're doing, you know. In fact, so I always give them credit where credit is due, because you know this, Bill. Yeah, you're one of the guys that got me to do this at all. Okay, you got me to do SkyTour live stream. You got me to do SkyTour radio. Okay, and if that guy wasn't doing it, then it wouldn't be happening.
Going under the table.
Yeah, well, it's true.
Isabella said it was RA364.
RA364. See, she is listening. Yeah, she's a tremendously talented lady and a great artist. You know.
But you also, because of what you do, the impact of that, what was it, an asteroid or meteor on the moon?
Oh, yeah. That was January 19 or 20th of 2019. Okay, lunar eclipse in January of 2019. We were watching it live. Moon was filling the field, and all of a sudden, okay, we saw a white flash right on the lower left corner of the moon at the height of the eclipse. The moon was red down there, and at first we thought maybe it was a video glitch or something. We didn't know, okay, because you don't hear sound, right? And so we thought it might have been a video glitch. And it turned out that we were one of only 5 groups on the entire planet Earth to capture and record a meteor striking the moon. We were one of the lucky 5, and so that was pretty cool. You can't plan that stuff, you know. It's just when it happens, right? So
lucky.
Yeah. Yeah, it was luck. It was luck. You know. So when we look at the universe, we think about all these objects near us and far from us, and you say, well, how do we even know the distance to these things? Okay. Well, there's a lot of ways that we find the distance to objects in our universe. Okay. And this is something known in astronomy as the cosmological distance ladder. It's the way in which things are determined, the distances to things are determined. And this determination is made, like I said, in a variety of ways. And one way, I just heard from Tara.
She's coming shortly.
Oh, really? Okay. Okay, cool. And the cosmological distance ladder is interesting because I worked in a program for several years in a big observatory that was actually specifically tuned to find stars near the Earth. And if you think about it, if you hold your finger out at arm's length like this and you blink your eyes, you'll see that that finger is moving against the background wall. Okay. You've just done what we do to find the distances to the nearest stars. What do I mean by that? When you're holding your finger out like this, okay, and you're blinking, left eye and right eye, you see that the finger moves against the backdrop of the farther wall. Well, if your finger is a nearby star and the wall are farther stars, then what you're doing is you're actually able to determine the distance based on the shift that it makes, right? It makes sense. And how do we make the star shift? Well, we observe it when the Earth's on this side of its orbit, and then we observe it when the Earth's on that side of its orbit. So we have a basically 186 million mile diameter spot to hit it from this side and this side, and these are the viewpoints from which we can actually then measure the star against more distant stars. And because the Earth's orbit is 93 million miles away from the sun, that diameter of our orbit is out. It's good out to about 300 light years that we can detect a star out about that far.
That's amazing.
Yeah, and that's pretty cool. And that gives us the stars in our nearby, what they call our solar neighborhood. And I think that's pretty interesting.
So outside our solar system, what would be considered to be the nearest star outside?
Well, most people know that the nearest star system to us is the Alpha Centauri star system. Now, that's 4.3 light years away. Now, that means light takes 4.3 years to get here from there. And the universe is really big. And people don't really understand how big the universe is. I did an exercise, which I put up on Facebook, actually. And the exercise took a very popular target, which is the target which is behind us right now on the screen here. Okay. It is this target right here. This is the Rosette Nebula. Beautiful. And within the Rosette Nebula, there are certain details. You see, for instance, you see this guy right here in the highlighted area that looks like a little pillar, right?
Mm-hmm.
Okay. A stalk of material sticking out. Okay. And then you see guys like this, these things sticking out. Okay. These little black dots. Those little black dots, all right, and this entire nebula in general is 5,200 light years away.
Wow.
So you're seeing them 5,000 years ago, right?
Wow.
However, I actually wrote a program, knowing that the distance, I wrote a program to calculate how big in actual size these objects are. So this guy right here that you're seeing, that little tiny stalk, you see the rest of the nebula around it?
Mm-hmm.
Okay, now if we look at the whole nebula, do you know where that little thing is? It's in the lower left. And it's literally a tiny, tiny little piece in the lower. I
see it. I do see it.
Do you see that?
Mm-hmm.
Yeah. That little tiny thing, which is actually, so small looking in the telescope and in our imagery here, is further away, or is longer, I should say, than Alpha Centauri is far away. So Alpha Centauri is 4.3 light years away. That little pillar, that stalk you're seeing right here in this image, is 4.8 light years in length. I'm not talking across the square. I'm talking from the little round bulbous tip down to the fairly dark base of it that you see. That's 4.8 light years in size.
Wow.
Okay.
So
Yeah.
what's the size of the entire? I mean, if that little piece, oh my gosh. I mean, I see it. It's in the bottom left where I could see it.
Yes, it's down there. I don't have a way of showing the
Yeah, I
arrow.
can see it.
Yeah. Actually, I do. Let me go into a
It's almost
I'll do a present here and I'll
like
show you.
8 o'clock.
Yeah, no, I'll show you.
By the way, Tara will be here shortly. She's messaging me.
Okay, good. Okay, so
okay.
All right, so here is. Let me get rid of this first. Okay, so here it is. Let me add it to your. All right, so now you see it over here, and so here you see my cursor. Okay, now I'm going to show you where this is. There's the overall size of this nebula, and this thing we're looking at is right here.
Yep.
There it is.
Yep.
That little thing is 4.8 light years in size. Can you believe that?
Okay,
That
so
is
that would be
amazing.
so that would be from Earth
to past Alpha Centauri by almost a whole 2 light years.
Little piece.
A little piece. Yeah. Now I have not measured this entire nebula across. I could and figure out the rough size. In fact, I could do that as we speak, but in terms of the size, that's going to be it's going to be at least 40 light years, 50 light years across, maybe more.
If you multiply that little spot and
now here's another thing to keep in mind. In this little area here, when we're looking at this little thing here, yep. And this little guy right here, okay, this I measured from here to here. Okay. Hello, Tara.
Hello, everyone.
Nice
Sorry I'm late to the party. Holy cow.
That's okay. That's okay. So from the base of this thing all the way to the tip, that's 4.8 light years, right? But that's the shortest it can possibly be, because what we don't know is if it's angled away from us or angled toward us, in which case this length will be longer, but it's projected. So this is the shortest distance it could be, is 4.8 light years. See, so that's what makes this so absolutely astonishing,
Ooh, cool.
Yeah.
Oh, I see where we were. Cool.
Yeah, we're at the rosette, and then I was showing Bill these guys right here. These are globules that are gravitationally condensing, and so they're being compacted, and there's hydrogen gas in there. There's other elements. There's dark dust, which is what you see here. This dark stuff is actually dust, and it's all throughout the nebula. You can see it here. And so what's going on with this is that this particular nebula has a lot of things going on. It had a star birth in the center. Okay, and if I zip us back out again, okay, if you look in the middle here, okay, see how the middle of this is like almost like looks like it's empty.
It's like a tube, sort of.
Yeah, this emptiness that you see here, okay, this is empty for a very important reason. It's empty because these stars, these young cluster of stars, their radiation has cleared the gas and dust and made this cavity. They carved it out with their very, very, very powerful radiation. And they also are responsible for making these stalks we've been looking at. So if we come back here again, really briefly, here's another one. Okay, here's another stalk sticking up. Notice it's pointing at the stars. This stalk we were talking about, it's pointing at the stars. Okay, and all over the nebula, you're going to find that you have little stalks pointing to the stars. And what's happening is the starlight, the bright ultraviolet light and energy, the radiation pressure from these stars is eroding the gas and dust. And where you have concentrations of dust and gas, like here, it's actually very, very much more resilient to being eroded. And so in the lee side, on the shadow side, all right, these areas are protected by this dense area. If this dense area got wiped out somehow, then all this would eventually go away. But these are protected, and so they tend to make stalks. They tend to make these pillars. You've heard of the famous pillars of creation,
Yes.
right? And
Cool.
that's an example of the pillars and how they're formed. It's the same kind of process. Really neat.
It is.
And so, but knowing how far away this is, like I said, I did I wrote the program to calculate how big this is in real life. And this thing right here, as I said, was 4.8 light years in size, which is it's longer in length than the distance to Alpha Centauri, which is amazing. And then these little guys, this is what's interesting. When I measured this tiny little dot, okay, this tiny little dot was 141 solar system diameters. In other words, go out to Pluto, make the orbit of Pluto. That little thing is 141 solar systems in diameter.
Wow.
And that's the small dimension. Okay. Now, here's yet another thing which is really cool. If we zoom in all the way, let me try and do that here, because right now, obviously, it doesn't look too hot. Let me see if I can zoom in all the way here, because I want to show you, like, if we zoom in all the way, okay, we eventually get to the point where we see 1 pixel, okay?
Okay.
Now, we can't really see that here, but 1 pixel is about this big, okay? 1 pixel on this image. And 1 pixel in this image, and we zoom back out, all right, and show you 1 pixel, just 1 pixel out of the 5,000 across that we have in this image is 5 solar system diameters in size.
Wow.
1 pixel. Now, think about the fact that as humans, we went to Pluto. It took us a decade to get to Pluto. Okay. And the fact that it took so long is just, and that's just going on a radial direction effectively to Pluto. Now, yes, it did gravitational assists from the planet Jupiter and so forth. But
why not?
Yeah, I know. Why not?
Why not? You're there.
It's there. Yeah. So that added some time for sure. But that got us to the final speed to get us out to Pluto. But once we got there, we couldn't slow down. So it was a Pluto flyby. And then it continued on. And now it's out in the Kuiper Belt. Okay. And that's the Event Horizon. I'm sorry, the New Horizons spacecraft that was out there. Yeah. So that's neat. So these guys named these globules right here are called Bok globules, and they're named Bok globules after Bart J. Bok, who was the astronomer that discovered them. And when I was getting my astronomy degree, Bart Bok taught classes, and I took classes from Bart Bok. It was amazing to meet that guy. Wow. And he was sort of a disheveled kind of guy. He had jeans that were too big, and his shirt was always half tucked in. Okay.
Those astronomers.
True astronomer. Exactly. A true astronomer. You're absolutely right. So, but that was what we endured. Okay.
Hey, Mark, those, and again, I apologize for coming in late, but those really cool pillars that you were talking about.
Yes.
Whenever I look at those, it's always counterintuitive to me how they're formed, because to me, they look like there's something just shooting up and out versus something being eroded away.
That's right. Yeah.
And so it's really cool how you explain that. So I appreciate that.
Okay. Yeah. Because these are the hot stars that are actually causing these pillars to erode. That's why they point. That's why they're pointing at the stars. See, the pillars are pointing at the stars. Yeah. That's a huge clue. Yeah.
Yeah.
See, this giant tendril is overall pointing, and it looks like this is sloping away. This is sloping away. It's almost like this here is dense and is resilient against the energy of these stars, but this stuff is being pushed back. There's a little dense spot that's formed here, and this little dense spot is, I can zoom in on that a little bit. So this little dense spot is actually resilient, but the rest of it's being pushed back in a way. See.
Mm-hmm. Is that solar winds, or what are those?
Stellar winds.
Stellar winds.
Yeah, yes. The winds from these hot stars are actually this cluster. Now, I also did an analysis of these stars, and these stars, like distance from this star to this star, and this star to that star. You think it's a cluster; they're all close together.
It's like on a flat plane. Yeah.
Yeah, well,
Triangle.
yeah. In
Mhm.
fact, the flat plane is the closest they could possibly be. Okay, like for instance,
Right.
if you look at this star and that star right there, okay, this
Right.
star might be here. Okay,
Mhm.
the star next to it could be way back
Correct.
here,
Mhm.
way out here somewhere. You know, it could be way out there. Well, but so when you see it next to it, if it happens to be in the same distance, that distance is the shortest possible distance that these can be, but you
Makes
can't
sense.
account for how close or how far away they are.
Not by their luminosity, right? Not by
Oh
how
yeah,
bright they are.
that's exactly right, because they tend to be about the same type of star, but some of them could have formed with a little more mass than others, and so they would have a potentially higher luminosity.
Mhm.
But the thing that's the same for all the stars is their actual composition, the way they're what they're made of.
Mm.
Okay, because they're made from the debris of the universe that came before, right?
Cool.
So, and
This
they're
is
made
cool.
from the materials. Well, everything you're made of, Tara,
Mhm.
is made in one of those stars. Remember, you know that.
We are stardust. It seems like you should write
Yeah.
a song about that or
I think
something.
there might have been. I
Might
can't
be.
remember.
Okay.
Yeah.
I'll
Mark,
look into
there's
I
that.
think
There's a question coming in from Donald that I find interesting. He said you can't go
Okay.
by size now because suns can develop in different sizes, just like planets, the
Okay.
mass of them. So even though something looks like it's the same size, that doesn't necessarily mean they're the same size.
that's right. So that's Donald Kunzer when he says, and you can't go by
Go ahead.
size.
Right.
Yeah. Yeah. Donald's a wonderful Sky Tour live stream, viewer. He's been there for a long time.
Mhm.
Yeah, you can't go by the size, and it's an illusion because in reality, because the stars are so far away, they are only ever points of light. That's all they ever would ever
Right.
be. You
Mhm.
can't see the diameter of a star. So when you look at this image right here, in reality, you shouldn't see any bright dots, like big bright dots. You're going to see tiny pinpoints that are less than a pixel in size if you could do that.
Hmm.
Okay. And the thing is, if you just had little tiny pixels here, and then there's that.
Hey, look, there we go.
Yeah. If you had little tiny pixels here, that was the pixel image that I wanted to share with you, in fact. Okay.
Cool.
Yeah. So if you had if you could do that, all right. Is that Odie back? No, not Odie.
That's Honey.
Honey.
Sorry.
Tara's dog, Honey's constantly.
It's supper time soon.
Okay. Yeah. See, and you're like, oh no, I got to get on the show.
It's all good.
This is an example. This is actually a piece of this photograph zoomed in really far, and this shows you the square pixels. Now, these exactly those each square is 5 solar systems in 5 solar system diameters across, but this only works. This only works for
Mhm.
this nebula because this nebula is 5,219 light years away. So because of that, and because that's the case, we can scale our backdrop there, our background, okay, and our pixels. Yeah.
That's pretty cool.
Yeah. No, it's cool. I see Bill has got bored and left.
Oh, Bill.
No,
Hey,
he'll be back.
he will. I have a question. You said that we couldn't really measure stars because they're just points of light,
Yeah.
except our own?
Oh, yeah. I mean, our own is not a point of light. We can actually see its angular diameter in the sky from the Earth.
Right.
It's about the diameter of the moon. It's a half a degree.
Okay. Yeah. Cool. Okay. I was thinking we could, but that's kind of like obviously we could, but
Yeah,
trick
no, it's
question
okay.
maybe.
No, not really. Not really. So yeah, I put this whole discussion with a long, interesting write up on Facebook if people want to see it. It's on Sky Tour live stream as well, and
Cool.
but this is an image I took actually just a couple nights ago.
Wow.
So yeah,
It's just beautiful.
It is so clear.
oh yeah,
It keeps blooming and blooming, and
I
it
know,
never
doesn't
fades
it?
away.
I know.
It's amazing.
You'll notice that you see different colors, right? I mean, this is sort of a reddish, and this kind of looks lighter. In fact, it's kind of sort of green, but you don't really see that too well.
You do on the inside a little bit.
Yeah.
Yeah.
Agreed,
So
Bill.
if we do like right here, you can see a little of the green.
Yes.
Mhm.
Okay. And the reason you see that, and I'll just do this, Okay, the reason you see that is because we're looking at a different set of or a different element in there that's showing us itself through the color. Now, the way it happens is hydrogen is the most abundant element in the entire universe. Okay, then comes helium, and then surprisingly comes oxygen. Right, and then carbon. Okay, which is why I say it stands to reason there's carbon-based life on the planet. But oxygen is the third most abundant. And when you have oxygen out in the interstellar medium, which is what this is that we're looking at here, okay, oxygen in the interstellar medium is going to be part of these nebulae where we see them. It's going to be part of the hydrogen mix that we see here. There's hydrogen all throughout the universe and galaxies primarily, and there's neutral hydrogen in between galaxies. But we also see many different chemical elements. If you take a spectrum of this, you'll see that there's more than just hydrogen, which is the red glowing gas, and oxygen, which is the greenish glowing gas. You're going to see other elements in here too. And that's because they were liberated in the countless supernova that came before this was ever a thing.
Wow.
Right here. Just incredible, And so this middle part of the Rosette Nebula is actually there's a lot of oxygen in here. That's primarily where the oxygen is. But when I say oxygen, does it mean we can breathe in there, Mark? No. This is just atomic oxygen. And in fact, when we talk about gas that's glowing, and when you see glowing gas, you have to immediately think hot.
Yes.
Okay? Mm-hmm. So these young hot stars, okay, when we remember your high school chemistry and even college chemistry, organic chemistry,
test.
Atoms have protons in the nucleus and maybe some neutrons, right? Mm-hmm. Protons are +1 charge. The electrons now are circling the atom and they're -1 charge. So for an atom of hydrogen, you have 1 proton +1 charge and 1 electron -1. So when you look at the atom, normal hydrogen atom, there's no net charge. It has no net charge at all. Okay. However, if you hit that hydrogen atom with very, very copious high energy, like is in these young stars, then it's usually ultraviolet. Yes, exactly. Okay. Radiation that's ultraviolet. Okay. So very, very high frequency radiation. The electrons in particular are energized by that, and they basically swell in a way of they have an orbit, right, so to speak, and they go into higher orbits. If you hit them with enough energy, the electron can become detached from the atom, and that's called ionization. Now,
and
ionization, and it smells good in a thunderstorm. Mm-hmm. But ionization, okay, then when ionization occurs, the opposite happens too. That electron will eventually fall back into the atom. So when it leaves the atom, it's hitting other things and colliding with other things. And when it does, it's losing energy. And then it drops back into the atom. As it drops back into the atom, as it loses energy, it gives off light. And in the case of hydrogen, that single electron dropping into the hydrogen atom gives off red light. So that's why the Orion Nebula is red. That's why this is red. That's why the Christmas Tree Nebula. That's why every nebula we see that's red, the Seagull Nebula, all these nebulas we see that are red, that's why they're red.
Mark, I got a question. And it may be a stupid question, but you always used to say there's no such thing as a stupid question.
Well, it depends who's asking.
No.
I got him. Now go ahead. There is. You're right. There's no stupid question.
Within these hot stars,
yes.
Is there any? Because this thing is massive. If this thing is like 50,000 light years wide,
well, maybe a little less than that, Bill.
Well, whatever. No, the entire whatever this cluster is.
Let's say overall it might be about 80 to 100 light years across. It might be more or less than that. I don't know. I'm guessing.
So in those hot stars, are there the possibility that planets are being created around these hot stars? Because you have all this different types of elements, mass, dust, all these clumps area. Is there any evidence that there's development here, or will this just fade out in time and die out?
Well, okay. These stars are hot young stars. They're only a few million years old, so they're not.
Mhm.
They're not going to foster planets at this point.
Okay.
They're carving this cavity here with their hot radiation, so they're most likely also uh, literally pushing away any material that might have formed around them that could have become planets. Okay, that's kind of what happens with these. So this will
Mhm.
not, in all likelihood, probably won't find planets there. However, there's other stars that may very well be near this region, and if it's bathed in this hot hydrogen gas, then it probably won't have any planetary capabilities that would support life. It could have planets, but there might be too hot a region.
Mhm.
Okay, everything would be warmed up pretty hot. But I'll
Yeah.
tell you this: down here in this dark region right there, see that dark region right there?
Mhm.
Maybe inside of there, and the James Webb would be able to tell us inside that right there, or inside one of these globules. Okay,
Yeah.
these dark globules will protect the interior from ultraviolet radiation. Why? Because, well, we talked about it with this pillar, right? When that pillar was made, that bulb on the end, that little bulb on the end of that pillar, okay, and that's this guy. Oh, sorry, that's this guy right there.
Cool.
The bulb on the end of that pillar, okay, that was a dense region, and the stars trying to erode it couldn't do it. So it was heavy enough and dense enough, I should say, massive enough, with enough mass so that the interior is protected, and its integrity is protected from the star's radiation. So, in all likelihood, it's possible that inside of that bulb at the end, and maybe inside these dark globules that we see here in this nebula, it's possible that there is a star that might be in the process of forming, and that star might also have enough dust and gas. Remember, these little tiny dots are, this little one is 141 solar system diameters in size.
Wow.
There's a substantial amount of matter in there, way more than you would need to make a star system of planets. You could end up having maybe 1,000 star systems in there. But again, we would have to temper that by how much hydrogen gas is in there and how many stars get made. If one star is made, that's wonderful, right? But on average, when we look at these stars here, right, see how far apart they are.
Mhm.
I mean, you might think, well, those guys are close together, but knowing how big this is at 4.8 light years, the average distance between these stars is over 8 light years. 8 light years
Wow.
apart. Well, I mean, Sirius is what, 7 light years away or so, 8 light years. So you see, Sirius is a bright, wintertime star, brightest star in the northern hemisphere. Well, what if you had a
Yeah.
few more? What if you were in a cluster with a few more? Well, then you might just see a bunch of Siriuses in
It'd
your
be
sky.
beautiful.
It would, yeah.
Hmm.
But you see the whole point, right?
Yeah.
So again, a simple nebula like this, which is not so simple, shows us an awful lot about the universe and can teach us a great deal about how systems form, how stars form, how gas moves. Again, the stars carve out the gas in the middle, push it out the side, right? This is oxygen in here, primarily in this inner ring. Okay.
Cool.
Oh, yeah. And then this is hydrogen down here. And it's all mixed together, all with this dust. Now, where's the dust come from? Who knows where you know where the dust comes
Yeah.
from?
Everywhere.
Yeah. Well,
When you're in Arizona, it's everywhere.
yeah.
The thing that's remarkable, you say everywhere, when you look at this and you realize how big it is, say 50 light years wide.
Mhm.
But there's
Yeah.
so much other space out there. It's
I know.
hard to comprehend
Yes.
how massively huge the universe.
Yeah.
That's right.
It's
That's exactly right.
incredible.
Yeah. And the other thing too is, as far as the dust you see here,
Mm,
this dust is all throughout the galaxy,
Mm.
right? There's tons of it. And where's it come from? It comes from, if you look at this diagram, this is what's called the Hertzsprung-Russell diagram. The stars in the upper right, you notice a star at the upper right? You see what its name is?
It is Betelgeuse.
Yes, Betelgeuse. And Betelgeuse, I don't care. Okay. But Betelgeuse,
Don't
or
say it again.
Alpha, oh, no, you're right. Alpha Orionis, okay, is possibly going to go supernova. Now, if you put Betelgeuse where the sun is, it would be the diameter of the orbit of Jupiter.
Wow.
Okay. In other words, it would be 10 astronomical units in diameter. Okay. The sun is just 1 million miles and just under, like 860,000 miles across. The sun is tiny. Betelgeuse is super massive, super giant.
So
Now,
if that goes supernova, that produces a lot of the cosmic dust?
Well, actually, it's making dust as we speak, because these gigantic supergiant stars, as they expand in the outer atmosphere, even though it's part of the star, it's all the way out at Jupiter. Okay.
Right.
And even though it's attached to the star and part of the star, it's hot, but it's not nearly as hot as the core of the star where the fusion is still going on. Okay. So in that outer reaches of Betelgeuse, you can still get things going on, which, in other words, make compounds and molecules out there, way out there. So Betelgeuse is making, there's a lot of carbon out there. There's oxygen, there's silicon atoms that it was made with. There's calcium atoms, magnesium atoms, phosphorus atoms that it was made with, that are all in that outer atmosphere. And you're going to get very complex molecules made in the outer atmosphere of Betelgeuse. When it goes supernova, those all get blown out and spread to the universe. It's like when stars die, they just go, okay, time to give back to the universe. And it goes, bleh, and it explodes and sends all of its guts out.
But even in death, it's creating.
In death, it creates the potential for new stars, and it keeps the cycle going. Everything you see in this
very
image,
green. Yes.
Yeah. Everything, it's a very green process. Everything you see in this picture, all right, was thrust here by a series of supernovas over time. And the series could be billions and billions, whereas Carl Sagan says billions of supernova. So billions of supernovae over time are what are responsible for all that you see in this image here.
Wow.
So it's really quite an impressive sight.
Incredible.
Yeah, and this is just one object of millions.
Exactly.
Millions. Yeah,
it's hard to comprehend, really.
It is.
How much is out there?
Yeah, it's true.
And it really does look like a beautiful rose with petals. It's
it really
so
does.
fun.
It really does.
It does.
Love it.
Yeah.
Some of the names of the nebulas don't necessarily look like what their names are, but this one does.
Yeah, that's true. And that's actually kind of a little I guess people come up with colloquial names for a nebula, and they never stick to the actual name. Okay. This is like NGC 2244, I think, or something.
Oh,
but you know what?
Or the rosette by any other name?
The rosette by any other name. That's correct.
Okay.
Yeah. And this picture was taken here.
Oh, cool. I know where that is.
A couple of nights ago.
Yeah, that was 2 nights ago. We took it here. And I show people this door because that door is Tara's artwork. She did a really beautiful job.
Oh, thank you. It was fun. It was a lot of work, a lot of hammering.
Yeah, I can imagine.
Did anybody ever guess how many caps that made?
No.
No
one has ever.
Not really even close.
No.
Wow.
Yep. Not even close.
But thanks for the tries, everyone. It's just fun.
Yeah.
It's just fun.
Yep. And then, of course, this is for you, Bill.
Aw.
Oh my God.
That's the tarantula that was in the building when Tara and Dale and Marianne went out one time.
Yeah. I had a little friend there.
Yeah.
He's beautiful.
Yeah, and they're actually harmless, Bill, but if you want to believe they're going to stalk you in the middle of the night, go for it.
Again, I never knew their alternate name was because Because that's what Marianne was saying when she saw it.
Yeah, that's right.
It
Oh,
was funny.
God.
Yeah. But I mean, it's beautiful
Middle
out
school.
there, you know. And when I first got out there, and this was the very first, not that, this was the very first thing that went in the ground.
The flag.
Flag, that little flag, denoted the center of this concrete slab.
Wow.
Cool.
Yeah. And, you know, I saw, views like this. It's like, oh,
Wow.
come
That's
on, you know. Yeah, I
It
took
looks
that. I
fake.
took that on the concrete. It's fake.
It looks fake. Come on.
It's
Photoshopped.
it's Chat GPT.
Oh my.
Yeah.
Oh, it's
No,
pretty.
no. So it was actually I took that on the slab the night that the concrete cured, because this was poured on one day, and then later on that evening I was able to set up a camera on here, and I started taking pictures.
It looks so tiny, that slab does.
I know it does. I know it does. But it turns out it's 11 by 11.
Mm-hmm.
And as it turns out, the telescope that went in there is this guy right here.
Looky.
Okay, and that's without its shield on the front. That the dew shield on the front is it makes the telescope look a lot longer.
It's there on the ground. You can see it.
There it is in the lower left. Thank you, in the left center. Yeah, and Tara, who's right down there, okay, is responsible for much of the maintenance that goes on this telescope. She runs out to the desert and takes
Me and
care of it.
Marianne.
And Marianne, yeah.
Yep.
Yeah.
It's fun. It's interesting. I've learned so much about telescopes and
You have.
astronomy.
You have. Yeah. And here's before I converted it to be 25 times fast. You see that round thing in the front? That disc in the middle of the glass?
Mm-hmm.
That's a secondary mirror. And that secondary mirror is what reflects the light back down. The light comes in this main entry, hits the main mirror, comes up, hits this disc in the middle, which is another mirror on the other side, and then it goes down through a hole in the center of the main mirror and out to things like cameras and telescope eyepieces and stuff. Well,
amazing.
I chose to convert this to to a system that would be a lot faster, and to do that, I added this black cylinder on the front of it. You can see there, and that red thing is actually the camera. Yeah. So
smile.
That's it. Smile. Yeah,
smile.
Smile,
hey, planet. Smile stars. Ooh, smile.
wonder who that is.
I know.
Okay. Yeah. And you can see this has the dew shield on it. You can actually see the shield on the telescope now. So now it looks like this big gigantic cannon. Okay. And effectively it is, it's a light cannon. It's the coolest thing, but again, it's neat. And we also have an all sky camera out there, which I'm heading out there in just about a week and a half.
Cool.
And I'm going to be adding a new all sky camera that I built. And that is this guy right here.
Oh, it looks pretty. It's nice and clean.
Yes, it is. It's beautiful. And the inside is very simple.
Wow. Okay.
Okay. That clear bracket on the bottom, I laser cut that. It holds my imaging camera. Then what's above is what's called a Raspberry Pi. That's the black thing. And then that little thing in the black smaller thing, that takes power out of the Ethernet cable. Your cable you plug into the wall for the network. Okay. Well, I'm running 48 volts through mine. And when it gets to the building, well, I can't put 48 volts into this black circuit board up at the top there because it only takes 5. So this black thing at the bottom is a splitter, and it takes just the data out, so I can plug the network cable into the black thing at the top there. And then that smaller black cable in the side is the 5-volt power supply. So that splitter thing takes 48 volts and drops it to 5, and then I can run the Pi.
Nice.
Wow.
That gives me the ability to run this cable 300 feet and have full power. Because it's a USB-C connector, and people that know how those work. You only get about 8 to 10 feet out of those at the most, and then the voltage starts to drop. And I was getting it to drop, and I just couldn't tolerate that. Not good. So anyway,
that's cool, Mark. That's exciting.
That's what we're doing. That's what I'm going to be doing. Yeah. So I'll be there from the 12th to the 21st.
Now you have room for 2 telescopes in that.
Yeah, but we're actually, when I go out there, we're actually scouting another location entirely. And the third location is going to be here. And out here, I'm actually putting a small system that I can move around with me. And it's going to be a solar telescope. So we're going to be doing sun
Ooh.
observations as well. We're going to be able to see the
Oh,
prominences and the flares.
and it's going to be built similarly to what you have out in Arizona.
No, it's going to be very different. It's actually going to be a tiny little enclosure.
Oh, really?
And all it's going to do is just go open up, allow the telescope to see the sky, and then
Wow.
close up. Yeah. And well, of course, it'll follow the stars and follow the sky. But it's only going to be meant for daytime use because we're going to use it to look at the sun.
I'm coming over to check it out.
so as far as your like elevation that you need for viewing with the telescope, you have it's more limited that you would need versus because it's on the ecliptic, right? The sun's always in the same path. You're not having to look at the whole sky.
Very good point. Very good point. So what it means is you would open the telescope to the north, okay, and to the south, right?
Okay,
So that you
yes.
have that wide swath of the ecliptic, the celestial equator. Yeah, exactly.
Cool. Okay.
Yeah.
I
It's gonna be
see.
really neat. So it's gonna be able to be quite a little system, and it's gonna be something that I could take out of here and move it to another location very quickly and easily. Might be able to move it in literally a day because I'm not going to be moving hundreds of pounds of equipment. I'm going to be moving just a few pounds of equipment, the telescope itself, the mount, and it'll be in like this little enclosure which you can just disassemble. I've already talked to a metal shop here in Connecticut, and they're going to laser cut it for me,
Cool.
and you can assemble it on site and have it running in an hour. It's the coolest thing. But it's a nice little automatic enclosure, and it runs using things called linear actuators. You know, the door closes on your door, you close it, and it goes and just closes softly.
Yes.
They look like little hydraulic rams.
Like a screen door sort of.
Exactly
closing
right, a
thing.
screen door
Mhm.
closer, yeah. Well, imagine if you stuck a motor in that so you could push that plunger out and pull it in. Okay, that's a linear actuator. It goes in one direction but under power and comes back under power. I literally laid on top of one of the two that I have here, and it literally pushed me right off the ground.
Wow.
Okay, because it lifts 600 pounds each.
Wow.
So I
cool.
got them when I was thinking about putting a big telescope in the building here. But I've since decided I want to do a solar observatory because I must get too much sleep or something. So I don't.
Why would you need? Yeah. Why would you need sleep?
It needs no rest.
Yeah.
Need rest.
Yeah.
But
So,
you can
you know,
always have. But wait, can somebody else operate that as well? Is that something that's going to be similar in the operation of it remotely, or?
yeah, I'm actually writing a user manual so that if somebody goes to use it, it's not quite as bulletproof as it needs to be yet. But once it's bulletproof, yes. In fact, the second Arizona observatory that we're going to put in, that one's going to be quite bulletproof. So we'll probably be able to allow people to use it and spend time on it if they want to.
Cool.
So the
That'd be
manual
neat.
I'm writing for that and the other telescope will be very similar. But because the one in Arizona is the first one where we cut our teeth, basically.
Learned a lot.
Yeah.
Mhm.
The first long distance one. I had one,
Yeah.
you know, when I had the dome here. Okay, it was 75 feet from me. So I could run out if something went wrong.
In the cold, yes.
And I did, as you know. Right. That's right. So, you know, that's what happens, you know. So, but the solar telescope will give us the daytime coverage, and the telescopes in Arizona will give us the nighttime coverage. And what's nice
sounds
is
fun.
wherever I go around the world doing conferences and talks, whether it's day or night, I'll always, hopefully, because of the weather, I'll be able to actually do a live solar stream or a live nighttime star stream and show people the universe. You know,
How cool is that? It's just so fun.
I want to be the next Bill Nye the Science Guy kind of thing. You know, because
You're the real deal.
but I think Bill Nye's. You know, I don't like when you see a scientist shouldn't go into politics.
Yeah.
Okay. He's into climate change. I understand, because we do have to worry about that. He's not wrong about that. We as humans do have the possibility of injuring our planet, and to say we don't is just kind of a ludicrous thing to say.
Mm-hmm.
But I don't want to get into any politics. There's other shows that get into politics, and my thing is, when you get into politics, you immediately alienate 50% of the people, and there's no reason for science to do that. You need 100% of the people, and that's what it's all about. So I stay away from that. So I think that he went down the wrong path, and he should just keep his mouth a little quiet. Doesn't matter what you think; it matters what you do, And so contribute to science, right? You know what I mean? Yeah.
Well,
So-
with that, we're close to a break.
We
No,
are.
we're not. Stop it. We are certainly not near a break. What are you talking about?
Time flies when you come in late. Wow.
That's actually funny. Time flies when I'm an hour late. No, you weren't an hour late. Okay. Just as I get here, it's got to go. Holy cow! I'm going to do that again.
I won't take it personally.
No, not at all. So, when Bill, of course, will tell us when we actually have to go to the break, which is probably in like a second ago.
Mhm.
It
About
is
now
time.
would be a good time.
Yep.
Okay.
Yep. So cool. Okay.
Stick with us, guys, and we'll be right back after these words. See you later.
Okay.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
As UFO reports come in from around the world, the Mutual UFO Network, MUFON, is there. We continue to explore new cases and build our massive database. We share our information with the world in a number of ways. If you would like to be part of our investigative team, you are always welcome. What could be more exciting than exploring the UFO question firsthand? Join MUFON, find your friends.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Yeah. Okay. Yeah. Okay.
That's hilarious.
Thanks, Renee. Renee Cruz. Actually, Renee Cruz is actually a faithful watcher of Sky Trail live stream. Well, look, when you're in science, you don't have time to go get a tan at the beach, right?
That's right.
Which brings up a cool point. These smaller stars, when we look at the Hertzsprung-Russell diagram I brought up before, if you look at the right side, that all the way down to the bottom right, you see those orange little balls down there? Those red balls down there are the smallest stars. They're M-class stars. They're very low temperature. They're very small. And in the universe, they have the most planets of any star because there's more of these stars in the universe than any other type.
Oh, just by volume or the amount, they have more.
Yeah, there's more of them.
Not that they produce more than the other ones.
Absolutely correct.
Okay.
There's more of them. Yeah.
Okay,
so
cool.
What's interesting is a planet around one of those stars. Okay, and if it's in the habitable zone, it's going to be tidally locked. It's going to do what the moon does to the Earth. It's going to have the same face facing the planet as it goes around the star. And that process of tidal locking is going to create a unique environment for any potential life. The reason is because you won't have change of seasons. You won't have tides from a moon, possibly. All you're going to have is the same thing day in, day out. In fact, day in is going to be the day forever. Same face for the side facing the star. It's always going to be noontime. And then at the edge of the star, it's always going to be sunset.
And that's where you want to be, right? Probably that spot.
I'll tell you why that may not be the case, but I would like to be there. And on
the dark direction.
Yeah, on the dark side, okay, you always have the stars, right? Now, if it has an atmosphere, the side facing the star is going to be getting really, really hot, okay? And what does a hot atmosphere do? It expands, right? And it also moves. And so you can expect you might have some winds on the side facing the star. And then on the back side, you're going to have cooler atmosphere, right? At least that's your thing so far. And then at the transition zone, that sunset realm on all sides, where all the photographers want to go on there, they buy that package from the realty when they want to come here.
You bet.
Yeah, you betcha. What they'll do is you end up finding out that on that particular side, when you have winds like that, the wind from the hot side is going to go racing over to the transition zone to mix with the dark side. The hot's going to face into the cold. The hot and cold are going to sit above and below each other, going to cause a lot of storm systems, possibly.
Inversions.
Yes, and you're going to end up with very, very high winds, maybe hurricane force winds at all times around the sunset side. In the middle of the hot side, it might be gentle, and in the middle of the back side, it might be somewhat gentle. So the question is, how could life evolve in such a region? Well,
tell us, Mark.
Well, of course, we don't know, do we? Because we only have one example to go by, and that's us, right? That's us.
But we speculate, right?
Yeah, we're speculating. That's right.
Okay.
But I'll say this: if we look at the way and the nature in which planets are forming, it's possible that we don't understand how resilient life in general can be. I'll give you an example. There is a planet that was found by the James Webb Space Telescope, and it has an atmosphere made almost entirely of hydrogen gas. Okay, and you think of Jupiter as having a hydrogen atmosphere, and it does pretty much. Okay, but they also detected other compounds that indicate maybe this is a water world.
Ooh, cool.
And then they detected another compound which only life produces here on Earth. Okay. And that was this disulfide compound. And this methyl disulfide was found in the atmosphere of this planet. And we know it here and it doesn't smell too pretty. Whenever the tide goes out at the ocean, that smell, that
Mhm.
disgusting stink,
Fishy smell.
the smell of the sea.
Hmm.
Yeah, that's the disulfide compound, and it really is the breakdown and waste products from countless sea creatures, plankton, and so forth that you're smelling. And
Yum.
we only know one place on this planet where that occurs, and that's in the ocean, and it's because of life. So the methyl disulfide is a very, very important compound.
But
You know,
I have a question. Do we smell it, or is it there because it's interacting with the oxygen air? Because we smell it when the water's back. I mean, is maybe I those stupid question things, but is it, you know, how do we know it's completely a water world? Do you have to have some kind of beach or something for that to be detected?
Or ocean.
Ocean, yeah, something or
yeah, I mean, we know that things we know that the ocean is a boundary layer to the air, and we know that things float on the surface, so stuff can come up and get wafted into the air. It's really not a very big deal, right, to find
okay,
it there, right?
that makes
So
sense.
yeah, I
Mhm.
think it's and the planet was actually one that uh, James Webb looked at. I'm looking it up right now just to get the specifics for you. I wasn't planning on talking about it, but it's okay. Um, all right. So anyway, I'll find it. But the point being that because this is another one where James Webb found methane and carbon dioxide in an atmosphere.
Oh,
That was K218b.
well, methane comes from cows, right?
Well, methane comes from geologic processes
Yes.
and waste product of life as well. Yeah.
So this is categorized as an exoplanet that possibly could sustain some type of life.
Yeah. In spite of the fact that it has a hydrogen atmosphere.
Wow.
Wow.
Isn't that crazy?
Mm-hmm.
So when I mentioned that we may not understand how life forms, well, this is an example of why that's true, because we're seeing a planet that we would never think could support life,
Mm-hmm.
and then all of a sudden, we could support life with this thing.
Mark, in a universal sense, where there's oceans, do you think there's the probability that they will have some type of life with the volcanic vents underneath? You know, it depends on how cold it is. But does it look
Yeah.
like the oceans is where we need to be targeting to look for the possibility of life on some of these exoplanets? Water
Um,
planets, water.
yeah. Oh, by the way, I want to correct myself. I said methyl disulfide. I meant it was dimethyl sulfide. I just got screwed up. So it's dimethyl sulfide is the compound that James Webb detected. My apologies. So to answer your question, Bill, um, when we talk about the potential for life and we think about an ocean, well, on the Earth, the life started in the ocean, right? And when continents were on this planet and grew on this planet from tectonic activity, that was another place for life to purchase a hold. It might have started from an aerial material like a plant or something, but then creatures, once in a while, because of the moon and tides, would be left high and dry for a while.
Mm-hmm.
Some of them certainly died, but others, over time, uh, you know, had a curious mutation occur that allowed them to withstand longer periods out of the water. And that mutation was followed by their adaptation to it. And that's evolution. And it's a slow process. It's hard to really understand how that really works. But when you have a creature that's habitually out of the water for long periods of time, it says, oh, the water's getting shallower. I'm going to swim to deeper water. And it does. Okay. So that might be what it does. But then every now and then, one of them is going to have a little brain fart and says, I'm going to stay here for a little while longer. And they get stuck in the mud. And then they end up surviving when the water comes back in and say, well, that was weird, but not too bad. I mean, obviously they're not conscious of that, but I'm just saying. So that exposure leads to mutations that can occur.
Evolution.
Yes, it's a mutation followed by adaptation is the relative definition of evolution. Okay. And it's happening now with other species on this planet. We're seeing evolution occur right before our eyes in dozens of ways here on this planet. The changes in habits of certain creatures, the changes of colors, mating habits, migration patterns. This is all part of an animal species changing to meet new pressures in its environment. Okay. And that could be a response to mutation in the environment, a mutation in their own DNA, causing them to act a little differently, do things differently, be able to withstand certain things more. And it was the mutation of fishes that would occasionally, like catfishes, that would occasionally end up being out of the water for some period of time when the water was low. And over millions of years, that fostered the ability for these fishes to start taking advantage of that. Because if they could get out of the water, they were free from their predators, right? Because at that time, there were no land predators to speak of. These fishes coming out of the water were among the first. So it was safer for them. So if they managed to get out of the water at the low tide regions, they would survive, mate, and make more of those fishes that would be out of the water longer. And so the ones in the water might get eaten and they can't procreate. They can't, survive. So by their behavior change, they ended up creating this new channel of life that could survive and adapt to being out of the water for a while.
Yeah.
And long term, this led to creatures walking on the planet on fins, okay,
It's
for
amazing.
a while. Yeah. So all the stars in this image here, except you see where it says O, B, A, F, G, K, M. The O's are the hottest and bluest, and the M's, of course, are the coolest and the smallest. Well, on this main sequence, okay, M stars when are determined by temperature. Okay, if they're fusing hydrogen into helium, they're on this snaky line that goes right down the middle of the diagram there. Okay, that's called the main sequence. But if they're done with hydrogen fusion, then a fairly bright star, like a G-type star like our sun, could end up being very bright and red and big at some point because it bloats after running out of hydrogen. And there's a whole process. There's a whole stellar evolution show I want to do to actually talk about how that works and show examples.
Cool.
Yeah. That's down the line. But, Tara, I think you're going to be joining us for a lot more time coming up here, I think, right? You're going to have more time in your hands.
Maybe, yeah. I think that we'll see. I look forward to that. There's always so much to learn. And even if I hear it once, sometimes it's the second or third time that I hear it, that it makes sense, or like, oh, I get it now.
Yeah, that's
So
true. That's true.
Yeah. So I love hearing about all
doubt.
this.
I know. I'm glad that I'm glad that you're into it as well. I think it's really important to understand. Really important to understand how the universe works.
Hey, I have a question.
Yeah.
You were talking about, the water world. That's so when we're looking for life, we're looking habitable planets. Are we looking for the gamut of it? Are we looking for just rocky planets, or like an ocean planet, or what about like Venus? That's clouds. I mean, can't we survive in the clouds in Venus? So,
Well, I mean, clouds of Venus are actually difficult for us because that atmosphere is 90 times as dense as ours. Okay, which is fine. But the upper cloud tops of Venus is going to be cold up there. But the chemical composition of the upper clouds in Venus are an issue for us because of the nature of Venus's past evolution. Venus has a lot of sulfuric acid in its atmosphere. That's obviously very caustic to all living things on Earth, and that wouldn't change if you were up there. It would actually eat into your ship, it'd eat into your spacesuit.
Nice.
You might survive a few minutes on Venus, and then once the stuff started eating in, it would just it would crush you, because it's the temperature. Well, the pressure on the surface of Venus is well, the temperature is like 900 degrees, and the
So it's
pressure
not.
is 90 times what it is here.
Oh, I apologize. It's not in the habitable zone in Venus, but I thought it's possible that we could make things that live in the clouds. But could we do things if we were to go to an ocean planet? Would we have to then bring with us ways to live in that water?
Initially, we probably would, wouldn't we? Because we wouldn't know what to expect. But once we got there, we would actually be able to figure out, oh, well, we can just use these natural resources in the water here and make our habitats. Maybe we find some shallows. Maybe this planet doesn't have tides. So let's go in the shallows and let's actually make some underwater habitats. Okay.
Cool.
Let's sink our spacecraft and make them, underwater habitats, only like 10 people on the surface. Why? Well, protect us from the ultraviolet radiation. If there's ultraviolet radiation coming from the star, it'll protect us. Easier than burying it underground, because you bury it underground, it'll do the same thing.
Right.
So we would make use and do that. I think that's a really cool idea, though. There's thoughts about doing that on the moon. You go to the moon, it's airless. So they have lava tubes on the moon. And lava tubes on the moon are these, ancient, basically conduits where liquid rock, molten magma went through in the early days of the moon, and then they drain out. You've been to Hawaii, about lava
Yes.
tubes. Did you visit any lava tubes when you were there?
Yes. Oh, they're huge.
Right.
They're
And
huge. Caves.
and-
They look like cave is what it looks like.
right, but they're long tube caves.
Really?
know?
And yeah. Mhm.
And tell us about the visit to the lava tubes. That had to be exciting.
They're they're in all sorts of repair. So some of them have had walls that have fallen in, and some you can walk for long periods of times in them. But a lot of plants can go in there. But it provides shelter and growth for a lot of animals and plants. So and they're beautiful.
Wow.
But they're very moist in Hawaii. Of course, it's a very tropical environment. But I could see, like, if you had a habitat on the moon, something that was enclosed, you could probably transform it to whatever habitat you needed, right?
Yes, you could.
Perhaps.
Yes, you
Mhm.
could.
I'd put a lot of plants up on the moon, bring a lot of Hawaiian plants, some pineapples. Be good.
Yeah, I believe that. See, and that's all good. And so, when you think about these lava tubes, okay, the lava tubes lend themselves to a particular ecosystem on the Earth, things that live in the dark, things that make use of the high moisture content in some of these, okay, and how dry they may be. There's all kinds of different ecosystems. Well, on the moon, you just have one ecosystem: dry, nothing.
And cold, right?
And yes, and it'll be cold. Only because the soil is cold in the dark. Okay, there's no air, so there's no temperature when you're in space. There's only radiation absorption into this and radiation emission off of this.
Interesting.
You only have absorption and emission in the universe, right, Bill? You know all about this.
I was going to say, just the problem. What was it? The one that tried to land a week ago? Innovative machines.
Oh, yeah, that's right. Innovative. Yeah, that's right.
Is it because of those situations? Because space is hard. It's hard to get these landers to actually land on the surface of the moon.
Yeah, that there's no doubt about that. No doubt about that. They actually were trying very hard. Okay.
Ooh.
Yeah, don't worry, we're getting to that.
Ooh.
And so what happened was it went to land, and then as it landed, it was landing like this, and it came across, and when it landed, it hit, and it was supposed to just kind of come down, all right? But it didn't just come down. It was moving horizontally at the same time. So when it landed like this, the landing gear snapped, and it fell over.
Whoops.
Over.
Yeah.
Darn it.
So that's what happened. But all the science packages were intact, and they could still do all the science.
Wow.
Well, that's the whole point, though, right?
Yeah.
Well, think about the achievement, though. a private company landed on the moon successfully.
That's
And
incredible.
3D printed.
Right. And now
Wow.
what that tells you is the following. It tells you that sooner or later, universities will have moonshots. And they'll be able to buy passage to the moon. And, there'll be like a large spacecraft, probably from Elon Musk, a Starship variant, will circle the moon and drop off payloads. And each of their little payloads will land on the moon. And then you'll have like University of North Carolina with their own moon lander. You'll have the University of Michigan with their own moon lander, right? You'll have Wesleyan University in Middletown, Connecticut, okay, where I got my degree. Okay, they'll have their own moon lander. They should get it first, actually.
Hey, so should I buy like one of those square footage little pieces of property on the moon? And so if they land on my spot, will I have hit the jackpot?
I wish that people could actually do that. I mean, it's kind of, if you think about it, it's like a romantic thing, right? Oh, I want to own a piece of the moon.
Yeah,
I get it. But
now, you mentioned about having Starship land there.
Yeah.
And possibly, what about mining because of the rare earth elements? Do you think it's actually profitable for them to mine Mark on the moon and send it back here on, say, a cargo vessel that provided by Elon Musk, SpaceX? Do you think it is profitable to do it that way?
Not at all now.
No?
No, not now. And the reason is because we don't have the infrastructure. How do you get the materials off the moon? You put them in a spacecraft, launch it off the moon.
Sounds like a joke.
It does. They're thinking about it. They all think about it. Like,
you guys walk into a bar with a load of ore.
A moon bar.
and they actually where do astronauts go to unwind?
Oh God, we should figure this out, Bill.
Gosh.
to the moon bar, the moon bar, yo. I don't know. Oh, come on, why don't I know?
Come on.
Think of your keyboard.
To the oh gosh, Mark, you're gonna have to tell us.
Yeah, come on.
Space bar.
Oh.
Duh.
That was a great clue too.
Oh my gosh. Sorry, folks.
So the thing is, okay, if you think about the prospects of getting to the moon, okay, it's already hard enough to get there. So we have to work out a way to get there easily, cheaply, efficiently, right? And it's going to cost a pretty penny to get there. It's going to cost also money to get off the moon. Now, what if you have to do it routinely?
Oh yeah, you have to.
What do you have to send packages of ore back to the Earth? Okay, how do you do that?
A moon cannon.
Very close, actually. And one of the ways to do it, Tara, the thinker over there, is you slingshot it off the moon using a mass propeller system. Okay, and these mass drivers are things that could send packages off the moon one after another at high speed. Where do you get the energy to do that? Well, you have to manufacture the fuel on the moon to do that. Okay,
but the escape velocity is less then, right?
That's correct. And so what you're going to do is you're going to aim it in such a way that the moon's own gravity is going to help you, and then it's going to allow it to escape the moon gravity.
Cool.
So each of these little packages has to have a tiny little thruster that activates at a certain time. Okay, now you see mounting costs here. So the easiest way to do it is not to send the ore back to the Earth. Easiest way to do it is to mine it on the moon, use it on the moon, refine it on the moon. Okay, so if you want to build a ship, to say go explore the outer solar system, at a certain point, you'll want to build it on the moon or in Earth orbit.
Cool.
Okay, if you build it on the moon, well, then you have ready access to the materials, the raw materials from which you can make all the metals and the other stuff you're going to need to create rocket fuel, to create the ship and the structure. And I can see how you could have 3D printers on the moon that use lunar soil ground up and processed to make spacecraft componentry.
Wow.
Okay, I can see how that could happen. Now, let's suppose you do that. Now you want to leave the moon to head out to Pluto on your spacecraft, which is going to go do exploration. Or no, let's say Europa. You're going to go to Europa because you want to explore the oceans of Europa.
Okay.
So you're going to build your spacecraft on the moon, and then all you need to do is to give it enough power to leave the moon's orbit. And that prospect is way easier when you don't have an atmosphere and when it's 1/6 of the gravity of the planet you came from.
Right.
So starting on the moon and with your final destination being the outer solar system is actually quite a lot easier in that particular way than starting on the Earth, going all the way to orbit and building it in Earth orbit and then trying to accelerate to get out of Earth orbit. The size of the rocket you need to get out of Earth orbit is substantial compared to the size you need to get out of lunar orbit.
Right.
See what I mean? So it would make a lot of sense to do that, to actually build in place and to actually then take and launch from the moon to your ultimate final destinations.
So that would be more the priority, to create a colony, a base on the moon that can then be the point of going outward into the solar system and beyond.
Correct.
Charles Schmar in chat says a new job, lunar brick catcher. I would do that. Charles, you and I can go up there and we'll do that.
That is funny.
There you go.
Lunar brick catcher.
That's great. That's great.
Yeah. Yeah. So, a lot of people have, have questions too. Like E-Man says, do you think the air is more than, do you think
there is more?
Oh, there is more than Earth intelligence, but it just takes turns after world. Okay. In other words, was there a previous world other than our own, here on this planet, like a previous civilization? There's no evidence of that at this point. And basically this planet has tectonic activity. Okay. Tectonic activity is activity that recycles the crustal plates. So you figure, well, if it recycles crustal plates, but the crustal plates, okay, the way they're moving and subducting, they haven't fully regenerated. So there would be some evidence of a previous civilization.
Oh, we can tell that?
Yeah, because we know the rate at which the Pacific plate is, or the North American plate is riding under the Pacific plate and stuff, or vice versa. So,
cool.
So it's pretty cool, Yeah, but I'll tell you, it's really neat. Let's see if anybody else. I see in the chat, there's a lot of people here, and then of course we do have a lunar prospector in the bunch, and that'd be Ronald.
Go figure. With the gold.
Yeah. Well, the truth is, there certainly will be gold on the moon. We just don't know where it is. And the reason I say that, Ronald, is because the Earth and Moon were kind of created roughly at the same time. Earth has gold. Gold was made by, potentially colliding neutron stars. Okay, that process, and then distributed to the cosmos over a long period of time.
A lot of neutron stars.
Yeah, that's right. Yeah, and that's the thing people don't understand. They don't understand that there are so many processes out there that took place that begat us. Okay, we came from all these many processes that came before us, and we know what 10 years feels like. Okay,
yeah,
but you'll find yourself saying, "Boy, that decade just came and went, and I didn't even see it happen."
Oh, right? I said that.
Right? Time passes so quickly. Yeah. However, just imagine if you lived a lot longer. What if you lived for 1,000,000 years?
Wow.
Why, I remember when I was just a kid at age 500,000,
middle-aged,
650 years old. I was just a toddler. Right?
Oh my gosh.
Yeah. Yep.
I like.
Think of what we'd see.
I agree. And E-Man, you got it. Justice for Pluto. I'm with you. I think I've told the story. I met Clyde Tombaugh, who was the founder of Pluto, and he and I were sitting on a grassy knoll up in Vermont, and we were at a astronomy conference, and he was going to do a talk in a little while, and he was sitting there, and I went over, I sat with him, and I said, Clyde. He goes, hi, how are you? Very unassuming guy, very nice man. Okay, was not a PhD astronomer, didn't even have a master's degree. In fact, he was self-taught. And
Nothing wrong with that.
he just liked astronomy, and he proceeded to dive in head first. He became a fixture at the observatory where he worked, and he ended up discovering the planet Pluto.
That's
Yeah,
so cool.
yeah, that was so that's incredible. So seeing justice for Pluto to me is also justice for Clyde, because they stole the planet from him and made it a dwarf planet. I know why they did that. I get it. Okay.
Because he wasn't in academia?
No.
Because he didn't have those degrees? Is that why they did it?
No. See, all the planets are kind of in a plane, right?
Mm-hmm.
Okay. Pluto's on a little angle like this, so it's going around like this, where the planets are kind of going around like this. So people, it's already different. Okay. So Pluto, also being smaller, appeared to be an icy body. And we know that beyond Pluto is the Kuiper belt out here, and then there is an Oort belt beyond that, and then an Oort cloud past that. Okay, the overall size of our solar system is literally about 2 light years in diameter, maybe more. Okay, so it's very possible that we've shared material with Alpha Centauri's star system and we'll never know it.
Wow.
Okay, yeah. So I think what's interesting is when you look at all this material out there and you look at the icy bodies out there, Pluto kind of does look similar. You have the plane of the solar system, you have this guy, we have other Kuiper objects which are going, at strange, orbits and so forth around the sun. Okay. And we call those near Earth objects, right? And they'll be fairly small, fairly large, like some asteroids, the killer asteroid. Yeah, the killer asteroid will be a near-Earth object. Okay, but Pluto just didn't seem to match the planet definition in the end. But I think out of respect for the find and for culture, I think they just should have said, we recognize Pluto's not a planet, but you know what? We're going to consider it the 9th object in our solar system. If you don't want to call it a planet, calling it a planet makes you cry, well then fine. We'll call it the 9th object, okay?
Item number 9.
Yeah, item number 9. Number 9. Number 9. Exactly.
Oh, my. And speaking of time going fast, Mark, I remember when we were having the discussion about the solar eclipse, which is
April 8th.
April 8th.
Oh, cool.
Yeah, April 2nd, I'll be in Danbury, Connecticut doing a talk on the solar eclipse.
Oh, fun.
Yeah. And I wanted to do it on the eclipse day, but the library said, we can't do it on the eclipse day. Why? It's a weekday. People are going to be working. No one's going to come. That's the day when it's going to happen. Now, in Connecticut, we're not going to have totality. We are going to have about 87% covered here.
Ooh, that'd be cool.
Yeah, that's at least what I see. So it'll be kind of cool. It'll be a nice day. You'll notice that when it starts to get a little dark, it's going to feel weird, but it's not going to be like dusk. It's going to be brighter than that, because until that last 10% of the sun goes, you don't really notice it, and people will just think that there's clouds over the sun. It'll look weird. The light will look weird. So
Mark, if you had a solar telescope, would you be able to then look at solar eclipses? Ooh, that would be so cool.
Get it done. Got to get it set up.
Yeah, I have to look at the funds in the Sky Tour kitty, because we have another telescope to get, and that's the priority. But if we can put a solar telescope in there and get that up and running, that would also be a very important addition, and it would round out our ability to do astronomy for the masses, because there are people that would watch during the day. There's people that watch during the night. Yeah, I mean,
Go to our website, folks. Become a Patreon member and help us out. And just
we are. This is. It's.
There we go.
It's skytourlive.com, skytourlive.org. You can get us either way. And if you want to talk to any of us, you can get us at contactskytour@gmail.com.
Mm-hmm.
So it's skytourlive.org, skytourlive.com. We also have a Patreon too that you can join. And Patreon is really cool because that would allow us to further what we do. Right. So we have a number of subscribers now, and you get some benefits. Like one of the benefits is things like this. Okay, this is a fully processed image of one of our shots, and if you notice,
oh my gosh,
this is
the Running Man.
The Orion, yeah, that's right, the Running Man and the Orion Nebula.
Beautiful,
as you've never seen it before, right? Because this is what it really looks like. Look at that.
Oh my goodness.
Yeah. And so when you zoom in, you actually see all this dust and everything. It's just amazing. Yeah.
You could just stare at that for hours and hours.
Well, the thing is, okay, it's neat. Now here, like this brown stuff is dust that is reflecting light from these stars over here. Okay. And you'll notice like this object right here, this is a really cool little nebula. It's got a little tiny black opening where it allows you to peer through, okay, at what's behind it. And it's illuminating dust in here. And then you see this green, this bluish glow here with this little line, okay, right there. Let me zoom in on that because that's actually kind of cool. This line of dust is up here in the foreground, and that light blue stuff is behind it here, okay. And so this dust is blocking what you're seeing behind it, and so that's why this looks this way, okay.
So pretty. And
this dust you're seeing here is elemental dust. It's made of carbon compounds. It's made of silicon compounds. All of the stuff that makes us what we are is from that type of situation. So this is, if people join our Patreon, these are the images that people can get from us. And they can take these and make them into literally, I've had people make them into wall-size prints. Like dentists, doctors' offices put these on the wall and say, wow. And we
That'd
just have to,
so cool.
Yeah, we just have to take them, and you can see the wispy clouds here. And by the way,
the detail's incredible.
This thing right here, this is about 24 light years across. So this wisp of dust is like 5, 6, 8 light years long, maybe 10 light years long. Actually.
Oh my gosh!
So if you were within that, you wouldn't even. It would look the universe would look normal to you. No, you wouldn't see it.
It's hard to believe. It looks like that's a helmet there on Orion.
It does.
I always think that's like a little helmet on it. It's still flying through space or something.
Oh, that's funny. So this is the helmet here?
No, down that right there, that white thing right there.
Oh yeah.
Yeah.
That's funny. Yeah, and what powers this nebula is primarily there's 4 stars in here called the trapezium, right. And they're actually made of more in there, but they are responsible, just like the rosette, for ionizing the hydrogen gas and making it glow red. And now you see this green out here.
Oh, it's so pretty.
This is a higher density of oxygen out here, and the oxygen glows green. And the dust is just brown. This looks like dust just floating through space. Now we're looking at this in 3D, remember? So there's a 3D, there's a 3D structure here that we don't really see. We just see the 2D projection. But this is the image I wanted you to see because this is a mosaic. We actually, I took an image of here, okay, then an image of here, then an image of here.
That's why it's so big.
And combine them all, yeah.
Mm-hmm.
Which allows you to zoom way in, you can go all the way in. It's like,
to the pixel.
Oh yeah,
look at all those stars. It's incredible.
Oh, yeah, there's all kinds of stars, little stars, everything in all these tiny stars. And somewhere in there, there could be the potential for there to be with a dark nebula. This is dark nebula that protects from the ultraviolet, remember?
Mm-hmm.
So the James Webb would show us, but maybe somewhere in here, this is all nebula, dark nebula here, there might be something in there, a planet. And that planet
People.
could have planets. And those planets could
What
have
can
life.
they use? What kind of methods can they use, Mark, to penetrate that, to see the objects behind it?
The James Webb Space Telescope is perfectly suited to look through these clouds because the James Webb is looking only at infrared radiation. So
Wow.
the infrared radiation it might pick up looking in these clouds is going to show all the stars in there that you don't see with your eye. Okay. And stars that the Hubble Space Telescope can't even show you. Now, Hubble has infrared capabilities, but not nearly as much as the James Webb.
Right.
So the James Webb could see the slightest warmth, which is what infrared radiation is. Okay.
And how much of the sky have we seen, Mark? How much has the James Webb looked at, and do we know about?
Pitifully little. You know, the James Webb has only been up there, and it can only point at one area at a time, take pictures, then move on. So there's maybe 30, 40, 50 photos that the James Webb has taken. And to do research, you have to look at the same object over and over again using different wavelengths of light that you're taking in. That all takes time.
Yeah.
You know, and James Webb's 1 million miles away, right? So that's substantial. You know, it takes light a couple minutes to get there. You know, a few seconds, a series of seconds to get there, but you know, it operates on a delay. You know, it's like me wanting to move the telescope when we had what was called HughesNet or Viasat. The speed was so slow that every time I moved the mouse, I had to wait 3 or 4 seconds.
Yes.
And then the mouse would then move on the screen out in the observatory. You know,
That's frustrating.
The reason was because the Viasat and HughesNet satellites were at geostationary location, 22,000 miles out. And the signal in orbit, right, 22,000 miles away. So we're always over the same spot on the Earth. So the signal would go out to them and then be transmitted back, right? And for that to happen, took time.
Right.
Yeah.
What about the laser communication that they're now using? Is that something that can speed up the process for communication purposes?
It won't speed it up, but it'll allow more data per second to go through. Because the waves, like when we communicate with a geostationary satellite, say by radio waves, well, that's light. It's traveling at the speed of light. Okay. So the speed of light isn't the thing. The volume of data carried in the light is the thing. Okay. So a laser can carry more data. The pipe is much bigger for a laser than a radio beam. Okay. So that is why laser communications can be revolutionary, because the volume of data per second is much, much higher. See, you know, so I mean, that's what's going on. This I have to say, this nebula is probably one of the most beautiful ones. It is definitely a winter sky object, you know,
very colorful,
so pretty.
Yeah,
it's like a watercolor.
I know, it's right there. It looks like a watercolor painting. It's right. Yeah.
Look at that.
This looks like spilled paint here. Yeah. Do you see the running man?
Yes, he's so cool.
There's the head, outstretched arms, outstretched legs.
Run away!
Run away!
He's getting away from that last supernova really fast.
Yeah.
Is this available on the website currently now? Is it?
To our Patreon subscribers, it is. I mean, the mosaics we make are available to the people that subscribe to us, but all the raw images are fully available to everybody. And we show people the raw images. We give them the raw images. And I think it's kind of important. Maybe what I should do is actually maybe kind of show that. That might be helpful. First of all, let me when I was talking about skytourlive.org, I think I could show you that and you can do that. Do you ever notice your arms and legs and hands don't work when you're trying to do something?
All the time.
Yeah, okay, so I'm not the only one. Okay,
All the
I
time.
resemble that remark.
I am. I do too. I know, but I'll show you what I'm talking about. So, bottom line is that when you look at stuff in the night sky, okay, this is Sky Tour. This is our website, okay, our portal. Sky Tour live stream here. This leads you to our channel on YouTube, and this is the stream from last night. Okay, that was a lot of fun.
Ah, that's a beautiful image. Some of those images.
Yeah. Oh,
Yeah.
it's amazing.
Oh,
Yeah, that's last night. Okay, and this is us right now. We're live on our channel right now.
Hi. Is this like Spaceballs and you have to keep
There you go.
licking?
That's right. Where does that happen in the movie? Now, sir. What
Now.
happened? Just happens now. When do we pass it? Take us back to then. I can't. Why? It happened. When? Just now. Oh. Really funny stuff.
This is blowing my mind. Okay,
Right.
cool.
Yes. And he goes across the floor. And he flips it up. I can't breathe in this thing. Rick Moranis' dark helmet. Oh, hilarious.
Oh, that's hilarious.
So
Sorry.
this is no, it's fine. Okay, you can see our latest stream here, which I'll change that link. And then if you want cool pictures, this will take you to the online database, and we have folders, and it shows you how to get to it. We have equipment giveaways. There's the telescope we give away. We gave away one telescope and 2 sets of binoculars so far. If you want photographic prints, you can actually go get prints on metal, framed under glass, on canvas. It's just incredible. And we have photo gallery of all the many things we've done. It talks about us, who we are, where we're located, everywhere.
Amazing.
Okay, so let's go back now. So if you want to get pictures, then it takes you to the online database, and the online database is a set of folders. Now, this was last night. Okay, we took pictures of the 37 cluster, the beehive, Christmas tree, a supernova, the crab. Let's start with that. Okay, this is the raw image that I'm going to show you. Okay, that everybody gets, right? If you want it, it's free. This is the Crab Nebula as seen by the telescope, right? Last night.
Wow.
And that's raw. It's
This
still
is raw.
pretty for me.
Yeah.
It's still beautiful.
Yeah,
Oh
and
my
you
God.
see that star in the middle there that I'm pointing to? That little tiny,
Yeah.
and that
Barely.
little blue star is a neutron star. This thing is thousands of light years away. This supernova remnant. It's a remnant of a star that blew up, and what was left behind was a neutron star that spins rapidly 33 times per second.
Wow.
You get that? 33
That's slow,
times
huh?
per second.
Wow.
Now, the star, however, is kind of small. It's the size of Manhattan Island
Oh my God.
in
Dense.
diameter. Okay. And it's so dense that if you could take a teaspoonful and get it to the earth somehow, it would weigh many billions of tons of teaspoon. Okay. It's really, really highly compact. And this was seen in the air in China in 1054 AD as a new star in the sky.
Is that
Right.
oxygen all around it?
Very good. This green is oxygen and the red is hydrogen gas.
Okay.
So this is stuff that is liberated in the explosion of the telescope of the star, because this was material that was in its envelope, the envelope of the star when it was made. Okay, so only in the very core of a star, you see my fist here, only in the very core of the star is where the fusion's going on. Then you got this massive envelope already all around the star that's just plasma, protons and electrons and so on running around. Okay, they are hot. Yeah, they're hot, and they actually serve as nothing more than a medium through which the hot radiation from the central core is going through to exit the star. Because there's it's mostly hydrogen gas in the outer envelope. So this is an example of the outer envelope being exploded into the heavens, and then the elements made in the core all the way to iron and are also blown out. There's new elements made in the process of the supernova when it happens, and how it happens is for another show. But it's really
Man, we got about 4 minutes. We got about 4 minutes.
I know.
Oh,
I
it
gotcha.
is another show. Aw.
Yeah. So the supernova are really interesting. Now, another one that we took last night was this one. This is called the Christmas tree and the cone.
Oh.
This is a beautiful area. This is the Christmas tree cluster. Here is a cluster of stars, and you see it makes sort of a point down to here. It's an inverted Christmas tree.
Right.
Okay. So the Christmas tree cluster is here. Down here is a feature called the Cone Nebula. It's a dark nebula right here, shaped undoubtedly by the hot stellar winds of stars either here or here. Okay. In that erosion process I talked about, probably had a lot to do with it. It might have had a lot to do with it. Yeah. Then up here, this really interesting cloud structure. This actually has a special name. It's called the Fox Fir Nebula.
Ooh, it must be very soft.
It looks soft, doesn't it?
Mm-hmm.
Yeah.
Yeah.
So that was last night, so
amazing.
And this all in here, this is dark nebula. This is that dark dust, an offshoot of this thing, which is a dark tongue of dust reaching up into here. Okay. And this dark dust, again, protects whatever's in it from the ultraviolet radiation of the hot stars. So it's possible planets with some form of life could take hold there. See? And so when we look at the universe, that's where my mind goes, And now when you have clusters where they have they're millions of years old, and now the stellar nursery within which they formed, their radiation has blown all that gas and dust away. Mm-hmm. Well, then you have a cluster that may look like this one. Okay, this is an example of one such cluster where all the gas and dust has been pushed away and only the stars are left behind.
Beautiful.
Okay. This is called the Little Beehive.
Beautiful.
Yeah. And it's called the Little Beehive, and it's in the big, the Orion's hunting dog called Canis Major. Right. And then we also image the real beehive, which is in the constellation of Cancer. And this is another one that actually liberated itself from all the gas and dust in its local area as it's pushed away it all. Again, these are millions of years old, each of these star systems in here. Isn't that crazy? So this is, let's go for a ride.
It looks just like a night sky. We don't see nebula in our sky, so it kind of looks just almost like a starry night.
Yeah. Yeah, it's just beautiful. And so this is, again, for me, this is the way I think that that astronomy should be. You should be able to have access to a dark night sky.
For sure.
And I'll be honest, you guys, I have not seen another stream on YouTube or Rumble that does what we're doing.
Right.
I mean, there's people taking pictures and streaming it, but I don't know if anyone is doing like astronomy talks and lectures and stuff like that live with the real universe.
Yeah.
It's you, the man. That's why.
Well, no, but it's why we say it's the universe live in real time.
That's right. That is true.
Yeah, and the thing is, I know we do.
We get to wrap.
Yeah, we'll be back next week, hopefully.
Yeah, we will. We'll be back next week. I want to first of all thank Bill for dropping in, saying hi to us, and hanging out with us.
Yeah.
I also want to say thank you to you.
Oh, thank you. Thanks, Mark. Thanks, Bill.
Yeah.
That was fun.
Sorry for the late notice,
Yeah, for Tara, it's like, hey, that wasn't bad at all. You know what though? You actually weren't that late. Actually,
no.
It was like only 10 minutes.
Yeah,
so that wasn't like a big deal.
Okay, good.
Yeah.
That's good because I always like to be here.
What I don't like is the fact that maybe you didn't want to do the show and maybe you didn't have time, but you're doing it anyway. I hope
pile of dirt up a mountain outside. She's doing yard work.
That's what I was doing.
I believe you, because you made a beautiful tortoise habitat for your tortoises. Hank,
I'm loving it.
We got to go.
Hank and Bruiser.
Okay, sorry. All right, folks. Thank you for joining us, and we will see you next time on Sky Tour Radio. Good night, everyone.
Bye.